my name is Ian Singer, and my project for the summer was to predicting the magnetic field components using wind and Parker Solar Probe data. And I mentored under Miss Samira Tasnim. Now, to start my project, well, before I got the chance to start it, I had to learn a lot about like certain components of the sun and solar weather. And one of the first things was, which was really key, was solar wind. And now, what solar wind is it's a phenomenon where the sun's corona, which is like is one of the outer layers of it, like the outer three layers of it. That's where the solar wind comes from, and we also call it the source surface. But what solar wind is, it's really just plasma that's ejected from the corona and sent out through space. And the thing about it is, it interacts with magnetic fields of other planets. And in Earth's case, when it interacts, it stretches almost and it creates the auroras, or as I know them, the northern lights. And those are at the two poles, the north and south pole of the Earth. And here's actually a picture of that. So as you can see from the sun, and it shoots out the solar wind right there, and then it's going to interact and create those auroras right there. And also with this, you can see the magnetic field around the Earth, which I'll talk about in later slides, and also solar flares, which will also be talked about in later slides. And as I mentioned earlier, so about solar storms, these are three different phenomena within them, which are CMEs or coronal mass ejections, solar flares, and solar energetic particle events. CMEs. Now, CMEs are almost like, from my understanding, they were almost like big explosions of plasma that came from the sun's corona. And I just thought of them as like bigger versions of solar wind, but they can move relatively slow and they can also go relatively fast. And the thing with these was they can be very damaging to satellites and also damaging to like different electromagnetic components on here on Earth. Like I think one instance was it like caused a blackout or something a real long time ago. And I think it was Europe, somewhere in Europe. Oh, and here's what that looks like. So the CME is the ring that's, as you can't see my hands, but it's almost projecting around in almost like a ring shape being pinched off of the sun. And it's that, I don't know how to explain, but it's like that big ring of fire that's coming off in a circular motion. That's what the CME is. Solar flares. Now, solar flares, all these really were like a quick burst of like energy, sort of, or that comes from the sun. And these kind of happen like really quickly, or they can last for hours, but they happen somewhat. They have something to do with CMEs, and they'll usually happen around them. So around the same time as a CME, you'll also get a solar flare. And this is the solar flare down here in this picture. That's what it's pointing to. Now, solar energetic particle events, these, from my understanding, these were really just sort of when charged protons from the sun will get projected from it. And these will also happen around it. These are also similar to solar flares, and they happen around CME events. And these are very damaging to spacecraft. So, moving on. Magnetism. Another big part of the project I had to learn about was magnetism. And in this presentation, I'm only going to focus on the geomagnetosphere, which is the magnetic field around the Earth, and the solar dynamo, which is the one around the sun. So the geomagnetosphere, this is the one where it connects from the north and south poles of the planet. And there are many, like, it's a pattern of space, like magnetic field lines around it. And this is what protects us from the solar wind and the CMEs and stops them from being so damaging to Earth, and also what is reacted when it creates the auroras. And the sun's magnetic field. Now, the sun is very electromagnetic, which I've learned throughout this entire summer. And it has a cycle where they're going to switch, like it switches the cycles from the North and South Pole. And it's way more magnetic than the Earth is by a lot. Now, here's sort of getting more into my actual project. I had to use, well, I had to learn about the magnetohydrodynamic models. And these are where a lot of the three equations that I use for my project are derived from these and the Maxwell equations, which I'll explain to you next. But here are the equations. So the first one is the conservation of mass. Second one is the divergence of the magnetic field. Third is Faraday's law. Fourth is the angular momentum conservation. Then the fourth is the frozen end field equation. And from there, we sort of goes into the Maxwell's equation, which is another one that a lot of stuff derived from that I used. And in that, you have Gauss's law for magnetism, Faraday's Maxwell Faraday equation, and Ampere's law. Let's go on next. And here are a lot of the variables that you're going to see used throughout the next equation. So in these equations right here, this is what the variables represent. And let me go show you. Now, these are the three main equations I use throughout my project, and these come from my mentor's paper. And the first equation shows the radial varying of the magnetic field, and then the second one shows the radial varying azimuthal magnetic field, and then the third one shows the azimuthal magnetic field at the source surface. And the source surface is just where the solar wind originates. So that's all it is. And then here is where this was the data that I collected from wind, and as you see, it's called the 1 hour average wind magnetic field data in GSE coordinates. GSE just meaning geocentric ecliptic coordinates. And the time period I used was from November 1st to the 27th in 2010. And then you see the 27 days because that's the amount of time it takes 27 Earth days for the sun to rotate on its axis. Here we have 1 hour wind, average wind data velocity calculated using flow speed and flow direction, latitude and longitude in GSE coordinates. Here, this is the location of the spacecraft that when they took it, and these are also in GSE coordinates and Earth radii in kilometers. And here are the results of my, when we run the data. So I'm just going to explain them based off of these. And we use equation 1 and wind spacecraft data to calculate radiomagnetic field. Figure shows the time and variations of BR and BFE at 1 AU. The plus and minus signs denotes the direction of magnetic fields. Results are in logarithmic scale. The transition between positive and negative values shows the sector crossings. Here, these figures show both azimuthal and radiomagnetic field components at the source surface. The field components vary with time by more than an order of magnitude, with BR being less than or equal to, no, BFE, RS being less than or equal to BR and RS at the source surface. And the magnetic sector and the magnetic sector crossings are more often due to the contribution of angular momentum conservation. Here, these just show radial variations of BR and BFE for a specific phi observation point. Radial variation of BR shows that BR is directly proportional to R to the -2, and radial varying BFE shows that BFE is directly proportional to R at -1 after 6 solar radii. Here are, and these are just time variations of magnetic field components from Parker Solar Probe data. Here's my discussions and conclusions. I have presented an analytic, self-consistent theoretical MHD model with a constant radial velocity, intrinsic non-zero B-phi RS at the source. The application of wind spacecraft data lets us demonstrate the existence of non-zero magnetic fields at the source surface, predict the values of BR, RS, phi S, and B phi RS, phi S. Extensions of the model for accelerating solar wind gives us the analytic characteristics variations with radial distance. Magnetic field components will be used to map field lines from the source 1 AU. And I didn't get to that in my project, and then the model's outputs can be tested using Parker Solar Probe data. And here's just a slide as to what I learned because I struggled a lot throughout this internship. So I learned that it humbled me because I was used to being a star student and easily picking up everything I do. And this just sort of proved that you're not always at the top and you can always learn something. And also that communication is important because throughout this, my mentor helped me very much, as much as she could, but I felt like if I communicated what I needed and where I was struggling better, I would have been able to learn a lot more and have been able to progress a lot more throughout this project. And that's the end of my presentation.
Hi, my name is Plasmy, and thank you for watching this video. Make sure to follow us on our social media at CPH2AL on Facebook, LinkedIn, and Instagram. Bye!